Hello students, we are coming to the second lecture, that is about the crisis in classical mechanics that have demanded quantum mechanics. There are some questions for which classical mechanics could not give satisfied answer. One of them is that why don't atoms disintegrate in nanoseconds? That is, how atoms exist safely. As you all know, from John Dalton, who discovered atom as the smallest indivisible particle in 1809, many scientists work on that and found that atom consists of fundamental particles like electrons, protons and neutrons. In 1911, Rutherford proposed an atom model by his gold foil experiment, but he fails to explain the stability of atom. It was pointed out by Niels Bohr, the colleague of Rutherford at McGill University, that Rutherford's atom should be highly unstable because accelerating electrons should continuously emit radiation and lose its energy and finally drop to nucleus. Bohr supplied a solution to this difficulty on the basis of quantum theory of radiation put forth by Max Planck in 1901. Thus, to the first question, Planck gives the solution by his quantum theory of radiation that electromagnetic energy cannot be radiated or absorbed in any arbitrary amounts but only in discrete quantum amounts. Each quantum is associated with a definite amount of energy which is proportional to the frequency of radiation, that is, E is equal to h nu, where h is the proportionality constant called Planck's constant, whose value is 6.626 into 10 raised to minus 34 joule seconds. Planck's constant makes a bridge between the classical mechanics and quantum mechanics. If this bridge is of zero length, we are in the domain of classical mechanics, where the macroscopic systems world we deal with physically. But when h is equal to 6.6 into 10 raised to minus 34, this means that we are in the domain of microscopic systems. By the Planck quantum theory, Bohr proposed his atom model for a stable atom in 1913, according to which, as long as electron in its particular orbit, it cannot emit or absorb energy. We will discuss Bohr atom model in detail in coming sessions. Max Planck put forth his quantum theory of radiation in order to explain the spectral distribution of energy radiated by a black body. What is a black body? A black body is an ideal body which allows the whole of the incident radiation to pass into itself and absorbs within itself this whole incident radiation without passing on the energy. This property is valid for radiation corresponding to all wavelength and all angles of incidence. Therefore, the black body is an ideal absorber of radiation. It reflects no radiation and appears perfectly black. It is also a perfect emitter of radiation. At a particular temperature, black body would emit maximum amount of energy possible for that temperature. That is, black body is always absorbing radiation, but when we heating it, it emits its energy. Blackbody radiation does not depend on the type of object emitting it. The entire spectrum of blackbody radiation depends only one parameter, the temperature. We should not expect a perfect blackbody. It's purely a theoretical concept, but our sun may be considered as nearly a blackbody as it can emit different radiations UV, IR or visible with respect to temperature. This particular concept can answer another question, that why don't hot objects emit more ultraviolet than they do? Classical mechanics couldn't answer this question because it considers light as a particle, according to which as temperature increases, the quantity of light only increases. But Planck gives quantum theory of blackbody radiation. According to his postulate, when a blackbody is heated, electromagnetic radiation is emitted with a spectrum corresponding to the temperature of the body and not to its composition. That is, at 4000 Kelvin, it emits red light, 6000 yellow light, and 18,000 Kelvin temperature, it emits blue light. That is, at different temperatures, it emits different energy radiations having a particular wavelength or frequency. This concept is extremely different from classical mechanics, which implies an increase in quantity in a definite energy. But actually, there are having different energies at different heights, which depends particularly on the length or frequency of radiation. Max Planck received his Nobel Prize for this in 1919. From that, wave nature of light was emerged, and to get a constant speed of light, we should change the frequency or wavelength of light. We can compare the speed of a radio wave and a visible wave. The visual wave having a 6 Hz of frequency and the radio wave having a 3 Hz of frequency. To get a constant speed, the visual wave should decrease its wavelength and the radio wave should increase its wavelength. That is, the longer the wavelength, the smaller should be the frequency to keep the speed of light constant. With this, I conclude my lecture, and I hope you get an idea of quantum approach of radiation, and we will go for the next failures in classical mechanics in coming sessions. Thank you.